we're chopping off, what, $500,000-ish?
You remember a guy, Ludwig Wittgenstein? He was a mathematician and philosopher that works under Bertrand Russell. And he was in the First World War. I think he was Austrian or something like that.
Oh, you said Wittgenstein?
Wittgenstein, yeah.
Ah, yes.
And
Logical positivism.
he was from a very rich family, if I remember. And his main work, he did it in the trenches, you call that?
Right, yes.
He was there and he was just writing when the first book that made him super famous in the philosophy world was written under bomb beams. I don't know how, it was pretty impressive.
Yeah, I mean, I know a little bit about his philosophy, and if you know that he was an engineer of some sort, you go, all right, yeah, his philosophy sure makes it's a very practical one. If you can't prove it, don't talk about it. That was one of the ones I remember. He worded it more eloquently than that. But Max?
Well, I'm not sure if it's right, but I got 0.088 or 0.087.
Units?
Meters.
So a diameter, so that's the radius, so the diameter would be twice that, so 0.174, ignoring rounding, meters. In other words, if the Earth could take all of its mass and shrink down to the distance between my fingers, it would become a black hole. It's sort of a fanciful thought because there's no reason. The Earth is not like there's pressure pushing out and pulling in, and suddenly it's going to collapse in on itself. Earth's relatively compact as it is. So anyway, the black hole.
Didn't you say it would become a black hole at 2,949 years? I thought you said it would become a black hole at 2,949 years. Maybe I misheard that.
That was the sun.
The sun. Okay.
This is the Earth. And every time I do this bit with the Earth, I always wonder, how dense could you make the planet? What is our capability of the densest thing that we could create? I suspect it's still not possible. Probably if you took the Earth and you compress it, if you could compress it down to that, you would start fusing nuclei, and I suspect the whole thing would blow up in some sort of atomic explosion. Mega hydrogen bomb. Or we create just one incredibly dense diamond. All right. I think, and also I'm pretty sure I did not do the ski problem. Okay? Kittens, ringing a bell? Okay. So let's do the ski problem. An actual math problem with energy. Oh man, that's just a little short. make it 50 meters tall. All right, so we have a skier. We're going to simplify this and just make it frictionless. Now, if this were just a straight ramp, then that would be a really easy problem, I would hope, at this point, for you to figure out how fast he's going at the bottom. But we have all sorts of curves here, and so I want to know how fast is he going at the bottom. We assume that his initial speed is close enough to 0. Again, I use the word speed deliberately because we're talking about energy here, which is not a vector quantity. And so in order to figure out about energy on this one, we really need to do a force diagram to start with. So I'm going to take this point here, and obviously change his drawing, or change the way he's standing, because there's only so much time I want to spend on drawing. So at this point right here, what are the forces acting on him? Okay.
Normal.
What else? Yep, all right. So we have two forces here. Weight. Conservative or non-conservative?
Non-conservative.
Right. And it's one of those two.
Conservative.
It is conservative. Normal force. Conservative or non-conservative?
Non-conservative.
So we now have a non-conservative force involved here. How is that going to affect us? Remember our work-energy relationships. We have non-conservative work is equal to the change in energy. The total work is equal to the change in kinetic energy, and the conservative work equal to the negative change in potential energy. So those are the three work-energy relationships, this middle one being the work-energy theorem. So, what is work? The calculus form.
Force by the distance. Force by the distance.
I'm looking for something more sophisticated. I mean, that's the gist of it, yes.
Force times distance times cosine theta.
What's theta?
The dot product of
That's what you're going with. Dot product of.
the force and the displacement.
Okay. So the dot product of force times displacement. What's the calculus form of it? So we'll just do force dot displacement. This is if force is constant. But if the force isn't constant, which in this case it would not be constant,
df dt? Would it be df dt? Since it's not constant?
no. I'm trying to think if you can work it into that. No, it's just generally not the approach taken. I should actually, you said dt or t, put time in there?
Yeah.
Yeah, I should say force is, if the force is not constant with respect to position, not time. Time's not an issue here.
I thought it was the integral.
Yeah, an integral.
Yeah, so it's the integral of f dot dx. It's the position which has the differential. All right, so we have this dot product between force and this infinitesimally small change in position. So at this point right here, what is the direction for dx? Dx is a vector. It has a direction. What is the direction of dx at when he's here? Okay. It's in that way. And the force that we're talking about here, normal force, is that way. When he's here, what's the direction of dx? Yep. And the force is that way. Let's do one more. What's the direction of dx? Probably bigger than it should be. What is the relationship between this force here, this normal force, and dx?
Perpendicular.
Therefore, since it's perpendicular, what is the work done by it?
One.
Nope, nope. You said one, right?
Yeah.
Okay, no, not one.
Conservative.
What is the dot product? Wait, sorry, louder.
Is it 0?
It is, indeed. Dot product cares about what's parallel. We're talking about perpendicular here. The force, the normal force, and the x, the change in position, that infinitesimal change in position, are perpendicular the entire way through. So, the work done by the normal force is 0 joules, if you want to throw units in there. So even though we have a non-conservative force, it doesn't do any work. Therefore, the only thing that's doing work is the conservative force. Energy is conserved, making this solvable. The work non-conservative equals 0, equals change in energy. And this is because normal force is perpendicular to dx. Now, if he happens to leave the slope, he's going so fast that he actually takes off into the air, at that point, the work would be 0 because of the normal force, because normal force would be 0 at that point. But while he's touching the slope, they are perpendicular to each other. Questions to hear before we actually start cranking through some similar stuff? Coming out with an answer? All right, energy is conserved. Oh, yes.
If there was friction, then it would be a different. Will it?
Yes.
Okay.
Yeah, friction would definitely change what we're about. Then there would be some non-conservative work being done, and energy would change. Other questions at this point? All right, so kinetic energy plus potential energy equals kinetic final plus potential final. Again, I am assuming that he is not bursting into flames. No spontaneous combustion in this problem. In other words, no mass energy conversion. All right, you've warmed up some with enthusiasm, everyone. What's the formula for kinetic energy?
1/2 mv squared.
There still seems to be this hesitation. Don't worry, you'll have other chances. Practice at home, practice in front of friends, family, colleagues. What's the formula for potential energy?
MPH.
All right, so some of you answered different questions. Let's try that one again. What's the formula for potential energy?
negative, big G equal,
Stop, wait. Answering the wrong question.
Which one?
There we go, that's the right answer again. The one associated with weight being the conservative force. Now,
MGA.
that's the one, yep, MGH. Now, the reason I do that is I, again, want to emphasize, I've had too many students in the past who automatically think potential energy, MGH, and that's not always the case. Trying to emphasize the fact that it does change. All right? And as before, what can we get rid of?
No.
All right? What else can we get rid of?
Initial velocity.
Right. And we can possibly get rid of one more thing, depending on how you want to work it. Anybody want to get rid of something else? And I will tell you, it's not this. Pardon?
The final height,
Why?
because he's gonna get to some point where it's gonna be zero at the end,
Why is it 0 at the end?
because he's already gone down 50 meters.
Not that reason.
and, like, depends on where you're saying zero is, I guess.
Yes. So why is 0 at the bottom?
Because
The origin.
Wait, I heard various things.
Like the origin, like axis.
yeah.
Yeah, but why is that the origin?
I was like,
Because
the
the axis
axis
starts
is
at the
at
point that you measure 50 meters up from.
where you wanted
I appreciate more than one person responding, but I really have difficulty there. All right, so Max, then Mario? People who begin with M, then Marisol, I guess.
Because you measure from that point up to 50 meters.
That's not the reason. That might be the
Wait, what
that's not the direct reason.
Could you say that again? I didn't hear you.
Because like that's the point that is measured 50 meters up from.
Oh, I was just reasoning that he had to start down at the ground and go up there, so that's the starting point at 0.
Now, there's a non-zero probability that he was created right there on top of the hill. I'm not saying likely, I'm just saying non-zero.
We're assuming the ground level is 50 meters below him, or the starting point is 50 meters below. Are we not?
Which get, well, apparently that seems to be what people are assuming. My question is, why are we assuming that?
Because we want to.
We defined it there.
Yeah.
Okay.
I mean, ultimately, Marisol spoke. It's because Marisol said so. You're powerful. We could have made 0 at the top. Could have made 0 in the middle. It doesn't necessarily make the math any easier, but generally you pick 0 to be someplace where you get rid of a term. So 0, because we say so. So we are left with this. GHI is equal to 1/2 VF squared. We're trying to find out how fast he's going at the bottom. In other words, we're trying to solve for VF. So VF is equal to the square root of 2GH initial. So 2 times 9.8. I am assuming this takes place on Earth. I believe it is a well-known fact that skiing only takes place on this planet, no other planet.
We don't know.
31.3.
So about 65 miles an hour-ish. Questions? Yes, Courtney?
What happened to the G on the other side? The MGH, what happened to that G?
Well, H, because I guess Marisol or several people made H final is equal to 0. So once that term is 0,
Oh, okay.
doesn't really matter. Other questions? I'm about to alter the problem slightly. All right, so now, he enjoyed that so much, he goes back up to the top. But he doesn't realize that there's a cave-in. UK is still 0, even though I just erased it. There's a cave-in right here. So he goes skiing down. Now, he is not hurt. At the bottom of this are cotton balls, clouds, and kittens. He doesn't land on any kittens. That would be cool. And of course, if it had been cats, he would have landed on them, and who would have cared? Who were the cat people I just insulted? This was the class which had no cat people. All right. How fast is he going right before he hits the cotton balls and clouds? Or how would you find it?
It's the bottom.
So the question should giving us the answer?
Yeah, 31.3 meters per second.
Yep, it's the same answer. Recognize the power of this conservation of energy is the fact that it is the exact same answer for this and for that. We know what the conditions are at one point, we know there's no energy loss, and so we know the total energy at the end. We do lose some information though. The difference is the speed is the same, the velocity is not. Questions before I change the problem slightly again? All right, so the kittens make sure he's okay, and then they show him a secret passage so he can climb back up to the top. And he gets to the top again. Meanwhile, there's a big snowstorm, it fills in and compacts nicely. Unbeknownst to him, the owner of the ski slope puts in a giant spring at the end, as ski owners usually do. Now, when you're dealing with a spring, let's make it an ideal spring. Part of being an ideal spring, it will not interfere with itself. So assume it's big, assume that it will compress, and that it's not like a slinky where the coils will eventually bump into other coils. When you're dealing with coils, it does take a certain amount of force in order to stretch them or compress them. So I have a slinky right here. It has a certain natural length to it. I can add hopefully something smaller than 200 grams. I wonder how well this is going to work. All right, so it naturally hangs from the coils there. Let's do metric. Roughly 3.8 centimeters. I add to the last one. So I'm adding 50 grams. Now, it's not hanging evenly, so I'm just going to measure to sort of a midpoint there. So it was, what, 3.8 is what I said before? And so now it's about 13.2 centimeters. So 50 grams. Nothing on it. It was at 3.8 centimeters, and this was, what, I said 13.2? Now, it's usually best to do several of these and not just a data set with this few points on it. I'm now adding a 20 gram mass. And please work. And it's about 8.2. 20 grams, 8.2 centimeters. Now, I am assuming that the acceleration due to gravity was roughly the same for both of those two masses, that I did not change it so radically in position that I can't make the assumption that G is constant. So technically, it's not the mass that pulled it down, it's the weight of the mass that pulled it down, but it still should still be proportional. So this 20 centimeters stretched it 4.4 centimeters. The 50 stretched it 9.4? Because this is 40% of that, the stretch should be 40% of that. I am off here because, well, it is physics and it was an impromptu demonstration. But 40% of that would put it at 3.76. All right? I will assume it is then. And we had 4.4. Also, it's not an ideal spring, but in an ideal spring, it should be proportional. If I can put a certain amount of mass on it to stretch it 1 meter, I put twice as much mass on it or apply twice as much force to it, it will stretch twice as far. So, ideal springs, and slinkies also, but have what are known as the spring constant, usually symbolized by the lowercase k. In essence, it is a stiffness constant. An example would be, say, 40 newtons per meter, which would tell me it takes 40 newtons to stretch a spring or compress a spring 1 meter. If I apply 80 newtons of force, it'll either stretch or compress it 2 meters, 120 newtons, 3 meters. It is directly proportional. The potential energy formula for an ideal spring. 1/2 K times whatever that stretch or compression is, squared. Obviously, I have not derived it. So the question I'm asking is, how much will he compress the spring? He's going to go all the way down to the bottom. He is going to compress it up to a certain point, and that's what I want to know. How much will it compress? Delta X final. It is a conservative force. What was the big indication that it is a conservative force? I shouldn't have had to say it, because I gave one other big clue that the spring is going to exert a conservative force. What was that big clue I gave?
That it's just a spring and it goes back to where it was.
If you wanted to start from scratch, yeah, that.
She said it was ideal.
Another clue, there's one other, I guess I gave 3 clues.
Yeah, it goes back to position with no dissipation of energy.
Okay, that sort of in keeping with what Max said. Sorry, spoiler. I gave you a potential energy formula. There are only potential energy formulas associated with conservative forces. All right, so energy is conserved. E initial equals E final. Kinetic initial plus potential initial is equal to kinetic final plus potential energy final. All right, you can do it. Chorus of angels, that's what I'm shooting for here. Chorus of masked angels. What's the formula for kinetic energy? So much nicer. Thank you. What are the formulas for potential energy associated with this problem now? Because we have 2 conservative forces, we got 2 potential energy formulas. And we have the one associated with weight, and the one associated with a spring, an ideal spring. And that's gonna be equal to, well, the same stuff except final. It's the final square plus mg, final. Plus delta x. Final. Squared. I didn't state it explicitly, but let's just go ahead and make the spring constant 40 newtons per meter for this. I do have to give you one other piece of information, which we did not need before, but we do need a mass this time. We'll just give them some generic 70 kilogram mass. That's my mass in ninth grade. All right, what can we get rid of? Or what's equal to 0? Either.
Initial velocity.
Yeah, initial velocity is, so you said initial velocity?
Speed.
Okay, initial speed is 0, so this first term drops out. Because v initial is equal to 0.
The compression should be 0 also.
Because the spring just sitting there.
Final height,
Why?
because the same reason we had last time.
Because we want it to.
Because we said.
We can actually get rid of one more thing.
Would the final velocity come to 0 once you compress that spring as far as you can?
If it's not 0, that means it's still, the spring is still moving and we want that maximum compression, that point at which he stops.